morning. Today we'll discuss one topic which is on the subject of computational fluid dynamics for 6th semester mechanical students. And the topic name is the nature or philosophy of the CFD and the process with which the CFD happens. Okay. Now here we are seeing one example of flow that is happening between two parallel plates. Okay, this is one parallel plate and this is another parallel plate, and the flow is entering from this side and leaving from this side. Now we'll take this example and we'll try to establish or we'll try to look into the general procedure and the steps that are followed in the CFD commercial tools or any other. This is generally followed in commercial tools, and the tools which may be done customized, they also can be followed in the same process. But these are the this is the outline of the CFD process which can be adapted by any code. Now the first aspect of the CFD process is to formulate the problem. Okay, so first we have to identify exactly what is the problem. Okay, here the problem is the flow is happening between the two parallel plates. So what we have to analyze in this particular scenario. So that is the first thing we have to look in. Whether we are interested in the friction between the fluid and the plate. Okay, or whether we are interested in how the velocity profiles is happening inside the flow. Okay, or any other criteria. What is the objective? What is the objective of the analysis that we have to first analyze? Okay, so the suppose here the objective is to identify for the given velocity of the flow how the boundary layer develops between these two parallel plates. So that is the objective for my analysis. Now what is the easiest way to achieve my objective? Okay, what geometry should be included? Here in the fluid flow, here we are not interested in what is happening to the plate and what is happening to the down plate, upper plate and down plate. What we are actually interested in is what is happening to the fluid that is flowing between these two parallel plates. So the geometry that should include is the flow, the domain in the CFD domain. What you call the CFD domain should include the space between the two parallel plates, but it doesn't have to be the plates doesn't have to be included into the domain. So that the geometry we have to analyze. Next, what is the easiest way to achieve the object? Whether I have to do a one-dimensional analysis, two-dimensional analysis, or a three-dimensional analysis. What are the operating conditions? Whether I have to take a free stream condition, or whether I have to take a pressure bound condition, or what are the operating conditions which are to be included in the problem. These are all the things we have to find out. Then if we understand what is the easiest way, then we can find out, we can finalize what is the flow domain should look like, how it should look like, and what is, whether it is a steady state problem or unsteady state problem, that also we have to find out. So what is meant by a steady state problem and what is meant by unsteady state problem? That is a important criteria. Steady state problem in the sense the parameters of the flow at this point and at this point or any point in the flow, if they are not changing with time, say suppose the velocity with which it is entering and velocity with which it is leaving, and what the velocities of the fluid at different points in the domain, in the flow, they are constant, they are not varying with time, then it is called a steady state problem. Say suppose if they are varying, okay, say I am heating the above plate or below plate or both plates. If I am heating that, so what is happening? The fluid is flowing through this and I'm heating. So because of that, what happens is the temperature of the fluid may change with respect to time. Okay, so initially if the heat input between top and bottom plates is constant, if this heat input is constant, what happens is initially it will be a unsteady state problem. After a particular time, what happens is the steady state is achieved. So what we are actually interested in, whether we are interested in the unsteady zone where the properties of the fluid are changing, or where we are interested in the steady state zone where the after the steady state phenomena is established. So what is our goal, whether we want the steady state things or unsteady state things, that is also we have to identify. Now next one is, what is the nature of the flow, whether the fluid is a viscous flow or inviscid flow. Means the viscosity, okay, the fluid is having any viscosity effects or the fluid is not having any viscosity effects. Say suppose if I take water, generally it is considered as a inviscid fluid, viscosity is very less. But if I take a oil or some lubrication oil or petroleum or any oils, generally the oils will while analyzing the flow of oils, we will consider the viscosity effects. So in some cases, like where the viscosity effects of water is also considered, then we can consider the viscosity flow. So whether the flow is viscous flow or inviscid flow, that we have to identify. The next one is whether the flow is laminar or turbulent. So laminar and turbulent means uh, say suppose the fluid is flowing like this without any mixing between the two layers of the flow, then the flow is called laminar flow. If there is a intermixing of the fluid is randomly flowing haphazard manner, so in this case it is called a turbulent flow. So whether we are interested in the laminar flow or turbulent flow, that also we have to identify. Then we have to establish the boundary conditions, initial conditions. So what is this boundary conditions and initial conditions? So if it is a unsteady state problem, then we have to establish the initial conditions, because at time t equal to 0, what these are the parameters. After a time t equal to something, the parameters will change. So when we are giving, we will give the initial conditions, and after a certain time we will get the boundary at the final conditions. The other way also, there are some say suppose I am doing one analysis like the fluid flow, and yeah, say suppose this fluid flow analysis only. So already I have done this analysis with some velocity. Okay, now I am doing this same analysis with another velocity. Now if I want, what I can do is I can give the previous CFD results as the initial conditions for this present one. Okay, so that is the way you can simplify or you can minimize the time taken for the analysis of the solution. Okay, now the boundary conditions, what are the boundary conditions, that also we have to see. What is the velocity at inlet, what is the pressure at outlet, what is the type of plate that we are using, whether it is a friction is it is having a lot of friction, or it is having is it a smooth plate, or is it a slippery plate. All those things we have to identify. Now in this problem, we'll see how to solve this problem. Okay, what are the how the domain should look like, all those things we have to see. So what is the problem? The problem is the fluid is flowing between two stationary parallel plates. Okay, the plates are stationary, so they are kept stationary, and we are throwing some fluid, we are allowing some fluid through flow between these two parallel plates. So that is the problem. Now in CFD, this we have three things called pre-processing, processing, and post-processing. Pre-processing means before solving the simulation, before starting the simulation, we have to create the model, we have to do the meshing, we have to give the solver inputs. All those things will come under pre-processing. The solving or processing, what it says is, once the all the things are established inside the black box, will start the run and it will solve all the governing equations at different points of the grid. So that is the solving process. Once the convergence criteria is reached and the solver finishes its works, what we have to do is we have to do the post processing. So the post processing involves the analyzing of the results and all those things. So we will see these three things step by step. So the first one is pre-processing. So what we have done is also sometimes considered as a pre-processing, because it is a part of pre-processing, or we can consider this as a step before the processing, pre-processing. So if you are considering about the computer software, then from here onwards what we do, we'll do on the computer or on the software. Whatever we have done in the previous slides, it is done before going on to the software. So before going on to the software, we have to find out what is the problem, what is the easiest way to solve the problem, what is the domain should look like, what is the flow parameters, uh, what is the type of flow it is. All those things we have to finalize. Once we have finalized all those things and step on to the computer or the software, we have to perform these three steps. Now the first step is the modeling of the geometry or flow domain. So here in fluid flow or heat flow analysis, what we are interested is in the fluid. Say suppose we have taken this problem, the fluid that is flowing between two parallel plates. Now here we are giving some conditions here on the boundaries, okay, but we are not interested in what is happening to these walls or the plates. Now we are interested in only in the fluid domain which is in between the parallel plates. Now you can ask me, sir, why previously you have shown the three-dimensional object, but here you have taken only two-dimensional object? So that is the interesting question. Say suppose the fluid domain is between these walls, okay? The flow is happening between these two walls, and say suppose this is the a cylinder, and the length of the cylinder is extending from this wall to that wall. So what is happening is we are not interested in the end things, okay? What is happening at the end of these two cylinders, at the end of the cylinder on that side or this side, we are not interested in the flow parameters at the ends. So what we will do generally in this kind of scenario, or in the problem that we have taken, we are taking two parallel plates like this, okay? We are taking two parallel plates and we are not interested in the the flow parameters outside this side and that side of the parallel plates. We are not interested what is happening. So that is the meaning of that is the length of these two parallel plates in this direction. Say suppose in the direction normal to this board, okay? If the length of these plates normal to the board are too large, then we are not interested in the ends, we are interested only in the center portion. So in such cases we can minimize the problem and we can say it as we can take it as a two-dimensional problem, because we are not interested in the ends, okay? Any problem like the flow over a cylinder, for aerofoil flow between two parallel plates, if the length is extended and we are not interested in the ends, what is happening at the ends are the tips of the of this boundary, the object, that the tip of the object, what is happening to the flow. If we are not interested in that, then we can consider them as a two-dimensional problems, okay? So this three-dimensional flow between two parallel plates is reduced to two-dimensional flow. So we have just drawn a rectangle, okay, and the top one is a wall, bottom one is a wall, and this is the inlet and this is the outlet. So the top one is wall, the bottom one is wall, the inlet is there, the outlet is there. So this the flow before the uh, between the the flow before entering the parallel plates, what is the flow is uniform. You can see here the velocity is uniform from top to bottom. Once it enters between the parallel plates, because of the friction between the fluid and the parallel plate, what happens is there is a generation of the boundary layer like this. Okay, the velocity profile will not be a uniform one, it will vary. And since the parallel plates are at rest, the velocity at the junction or at the parallel plates will be less, and the velocity at the middle of the parallel plates will be maximum. So that we have to see how the velocity profile is varying between these two parallel plates. Okay, now, so what is the approximation that we have done here? We have done the approximation saying that the 3D problem can be approximated as a 2D problem, because the tips or the ends of the parallel plates we are not interested. Okay. Now, the extent of finite flow domain in which the fluid to be simulated. So, the same thing. So, whether we want to make it a 3-dimensional or 2-dimensional, the proportions of the boundary of fluid element coincide with the surface of the geometry. Okay. So now here, say suppose it is a flow over a cylinder. Then what is the case? We need the flow domain should be like this. Okay. This is the cylinder over which the flow is happening, and this is the domain. This is the inlet and outlet. Now in this case, what should be the length? Whether it should go up to the infinity, what should be the distance of the cylinder from this free stream? Okay. So generally what is the case is, the distance should be such that these effects, the far field effects are, the far field is not having any effect, any reasonable effect on the flow over the cylinder. So it should be it should be adequately enough, and this comes by experience. Okay. So this the distance, or sometimes what they will do, they will try initially what they done, there was no experience. So what they have done, they have taken small distance, they have taken small distance, and they have analyzed, they have found some disturbance because of the field here, so they have increased, like that they have gone. So based on the literature, what we can do, we can find out, because already they have done, we don't have to do it again. So from the literature we can find out what is the distance, and we can analyze the simulation, when we can analyze the flow here. So this is the first step. What we have to do, we are the real domain is given, the parallel plates are there, the heights of the parallel plates, the lengths of the parallel plates are there, the widths of the parallel plates are there, the distance between the parallel plates are there, all these things are given. So what we have to do, based on those things, we have to find out what is the domain which is required for my simulation. Okay, so that is the first step. So the next step is other surfaces, free boundaries which over which flow enters or leaves. Okay, so say suppose this is the okay, we'll see one aerofoil we can take. Say suppose this is a aerofoil. Okay, the fluid is flowing over this. Say suppose we are analyzing only the flow over aerofoil, then we'll take like this. Say suppose we are doing some cascade analysis. So what is the mean by cascade? Series of aerofoil blades are there, and in between those aerofoils the flow is happening. So what we will do then, we'll mimic the surface like this, and we'll mimic that surface here, and we'll make the domain like this. Okay, so the based on the the flow, I mean the region of the flow, how the adjacent boundaries of the flow are, I mean, are affecting, I mean, are affecting on the flow. All the boundaries are to be taken into considerations. Okay, whether they are free boundaries or they are having some influence on this, whether these are moving boundaries or fixed boundaries, all other surfaces which are there, all those things we have to incorporate in our domain. Next, the geometry and flow domain are modeled in such a manner to provide input to grid generation. So, this, why we are doing this exercise, we have to, in CFD, what we do is we will take the domain, we will discretize or divide the domain into sub parts or minor parts called grid. Okay, so for this domain should be such that it is easy to grid it, or it is easy to do the gridding or the breaking into the pieces, or grid generation or mesh generation, all those things are same. So the structure and topology of the grid generation, so this is the topology I have explained. So all those things we have to fix. The modeling is done. Now what we have to do, we have to do the grid generation. So the flow domain is to be discretized into a grid. What do you mean by grid? You can say it as a, say suppose a rectangle is made into parts. So like this. This is called a grid, or you can sometime you can use the triangular one also. So the rectangle can be divided into triangles like this. Okay, like this we can divide. And sometimes what we will do, we will take a small one here and bigger one here. Like this we will divide the entire grid into the minor parts. This is called grid. So we have to do that grid. So how to do this? So there are techniques called multi-blocking, structured grid. So what do we mean by multi-blocking structured grids? So say suppose uh, one aerofoil is there, okay, and the domain is like this. So what I can do is I can break it into two, I mean, number of blocks like this. Okay, so the region near the boundary of the aerofoil, I can make it a fine grid. Okay, the fine grid, the size of the grid is very small. So like this I can make it very small. And for of this aerofoil, I can make a bigger one where the boundary layer effects are not there. So in that way I can use the multi-blocking. And the structured grid means the structured grid I have shown just now. It is a rectangle or hexagon type, rectangle or square kind of things, they are called structure grids. Unstructured grids are triangular grids, like that. Now the minimal bad quality. So the bad quality, say suppose the grid is like this. So this element is not connected in one point. This kind of bad element should not be there. Okay. And orthogonality. So what do you mean by orthogonality? So orthogonality means the orthogonality, skewness, all these things are there. So these two are at right angles, and in the domain sometimes this 90 degrees, making it as a 90 degrees is not possible 100%. So there are some some leniences or some some acceptable values are there of this orthogonality. How much angle is accepted? Say suppose this is the grid, instead of a rectangle it is a parallelogram, and what can be the maximum value of this or this? So this is the orthogonality. So the orthogonality must be there, okay, to the acceptable limits. Then the skewness in the sense the grid, okay, the grid is elongated or extended in one direction, then it is called skewness. Okay, so the orthogonality, skewness, they are all dependent. Now what is the relative grid spacing stretch? So the relative grid spacing, it is the exceptional limits are given here. These are the acceptable limits, they are 15 to 20%. Okay, 20% of stretching is allowed. So the grid space, say suppose like this is there grid, so like this another grid is there, like this another grid is there. So this the distance, this stretching is not accepted. Up to your whatever you want, you cannot stretch it. You can stretch only up to some acceptable limits. So the this is the grid for our flow between that flow between parallel plates. So the length of the grid is there 20 mm and the height of the grid is there 20 mm. So say suppose, I mean, say I am saying it is not 20 mm. What I have done is, this side I have made it into 20 pieces and this side I have made it into 20 pieces. Now here the distance is small, so we got small pieces, and here I have a longer distances, and so I have the longer pieces. So the total number of cells I obtained is 400 cells for this flow between two parallel plates domain. Okay, this is an example for the structured grid. Now the maximum spacings between should be consistent with the desired resolution of important features. So what is this meaning? Say suppose the aerofoil is there. So over the aerofoil there will be some boundary layer like this. So the boundary layer length will be very small. It depends on the y plus value, and the y plus value depends on Reynolds number. So the Reynolds number, we have to calculate Reynolds number. Based on that, we have to calculate y plus, and based on that, we have to find out what is the first layer thickness. The first layer, what is the distance of the first element from the surface. So that is called the first layer thickness. So what should be the first layer thickness, that also we have to identify. Based on that, what we have to do, we have to see that the first element is within the boundary layer in all the regions. Okay, so like that we have to identify the spacings. Okay, so after that we can increase the space. Here with the small one is there, so we are increasing the distance and we are making it bigger. So the resolution of the boundary layers required, so this is what I explained. And the turbulent flows and laminar flows also we can consider. Generally most of the cases will be turbulent. Very rarely we will see the laminar flows. So the turbulent flows, we have to see that y plus should be less than 1.0. Now what we have to see, how the space marching and time marching techniques are used inside the simulation. Okay, what should be the time, say suppose 1/10 of a second. So the time gap between the two iterations is 1/10 of the second, or 1/100th of a second, or 1,000th of a second. Like that, what is the time gap, time between two iterations? So that is that we have to identify. Okay, and the space marching, this we have to identify. And what is the turbulence model or chemistry model, or there are many models like k epsilon, k omega, sst, uh, and like that we have large eddy simulations, les simulation. Like that we have many models are there. Okay, so which type of turbulence model we are going to use, whether if the energy, say, if temperature is involved, we have to consider the energy also. So like that, what type of model we have to, we have to specify, that also we have to do. Next, we have to give the input data to the file. So already we have identified what is the inputs for the before stepping onto the system, we have identified what are the inputs, what is the inlet velocity, what is this, what is the pressure at outlet, what is the surface roughness values. All those input values we have to give, and we have to supply the grid. We have just now we have uh, discretize the domain, that grid we have to supply to the solver. All these things, say suppose if I have any initial input, say suppose I have done one simulation and I am repeating the simulation with a small modification of the boundary conditions, then I can give the previous results as the input or initial conditions for the present simulation. So that also, all these things we have to supply to the grid. Now here we can see the boundary conditions specified here. What is the velocity of this plate? Velocity is 0 because it is a stationary. The temperature, heat flux, is there anything is there? We are not interested in heat transfer. We are interested in only fluid flow. So the temperature is 0, heat flux is 0. Now what is the density of the flow? Is there a inviscid flow or viscid flow, that we have to see. And what is the velocity of the flow? And what is the temperature at the inlet? All those things we have to given. And the flow, whether the flow is happening in this direction or in this direction, that we have to see. That velocity direction we have to give. Then at outflow, the outlet condition, whether we can give a pressure condition, or you can give as a mass flow condition, or you can give as a outflow condition. Like this we can give some, give this boundary conditions. Now once you have given all the boundary conditions, we have discretized the domain, we have created the domain, we have discretized the domain, and we have given the inputs, initial conditions, and we have given the boundary conditions, and we have set up the convergence criteria. So all these things are done, then we have to set up the convergence criteria. So what is the convergence criteria? Say suppose here we'll see. So the error, we have x momentum, y momentum, z momentum, like that, and mass and energy, all these things, all these values must be simulated to a certain error. So what is that error? Acceptable error for all these values. Say sometimes they will give 10 power minus 5. So the 10 power minus 5 error. So what is the error means? I have done one iteration, I have done another iteration. What is the difference between these two iterations? The values of this iteration and the values of these iterations are compared, and the error between these two is 10 power minus 5. Then the solution is converged. So this convergence criteria we have to give. So once the convergence criteria is given, how many iterations, maximum iterations? Say suppose the convergence criteria, it is not reaching 10 power 5, 10 power minus 5 and convergence criteria. So can I go eternally? So I cannot go eternally. So I will define the convergence criteria, or I will define the maximum number of iterations that I am having. How much time I am having for this simulation. Okay, I have to compromise between those two. And then once these things are done, I have to monitor the simulation, monitor the solution till the convergence is happened. Say sometimes what happens is the error keeps on increasing, instead of decreasing, the error keeps on increasing. So if the error is increasing, it is called divergence case. So if the solution is diverging, what I have to do? I have gone somewhere wrong with the in conditions, inlet conditions, boundary conditions, or some grade. Somewhere I might have gone wrong. I have to stop the simulation. I have to go back and I have to check all the things, and again I have to start. Okay, so the monitoring means these errors should go on reducing. If they reduce up to some extent, after that there is no reduction, they are stable, then I can stop the simulation. So that is what shown in this figure. So you can see here the error values are keep on reducing. I have given a 10 power minus 5 criteria, and the results, I mean the errors have reached that criteria, so the simulation ended there. Once the simulation is done, what is the next step? I have to analyze the results. So that we will see next. So this process is called the post processing of the simulations. So what is the say suppose what is the thrust, what is the lift, what is the drag, etc. All those things can be calculated in the post processing. Now I have to make comparison. So I have to make comparison of these computational results with some experimental results or previously done experiment CFD results, which are already authorized CFD results. Then I can say that my computational values are accepted. Okay, so this is called validation. So the validation should be done. Then only I can say that my results are correct. Now the post processing can be, here I have shown three different types of post processing. This is a XY plot. So what do you mean by XY plot? So this is the two parallel plates I have. So from here to here, okay, this is the Y distance, and in the X distance, I mean X direction, I have velocity. Now with the distance from the wall, say suppose this is a distance, here it is 0, here it is a h by 2, and again here it is a 0. So with the change in distance, I have to find out what is the velocity at particular point. So at entrance it will be like this, and at midway it will be like this. Once the fluid is fully developed, the profile will be like this. So this kind of results, if I am showing it, is they are called XY plots. Another way of showing the same results is there. So that is the vector. Okay, this is the vector graph. So here what I am doing, instead of putting the dots here, from bottom to top, what I am doing, I am representing the values with some arrows, and the length of the arrow is proportional to the magnitude of the velocity. So this is the vectors, this is called the vector plot, and this is called the contour plot. So here we have given as a vectors. Now here in contour, what I am doing, I am identifying all the regions with the same velocity. So this blue color line is showing, it is showing that it is approximately 0 velocity, and the red color zone, the intermediate core zone, it is showing that the maximum velocity is during that region, I mean in that place, and the yellow, green, all different shades. So each color is representing a particular value of velocity, and this the contour plot is showing in which region what is the velocity that is prevailing in the solution. So this kind of three types of plots I have shown here. You can do any other, I mean way also. So generally these kind of plots are shown. Sometimes what they will do, they will give contour, I mean like this. Like this, they will draw the streamlines. Okay, they will take the aerofoil here or the cylinder here. Over the cylinder, there will be some points which are having the same velocity. Okay, so from here to end, they will join all those points, the streamlines, and say suppose this particle is going from here to here. So what is the path traveled by this particle? So these path lines are also can be uh, drawn. So these are the different ways I can represent the results. Now if the process is, I mean if the results are acceptable, so I can stop it. Otherwise the results are not acceptable, what I have to do, I have to repeat the process. So what I can do, I can change the dimensions, I can change the flow conditions, I can change the boundary conditions, or I can change the strategy, marching strategy, the time marching or the space marching strategies, or I can change the turbulence models or any other model I can use. So like this I have to do iteration, and finally I have to come to some conclusion. So that is about the post processing. So if I draw in a flow chart type of thing, this you can write like this. So this is the pre-processing, this is the solver, and this is the post-processing. So in the pre-processing we have seen creation, meshing, properties, boundary conditions, all those things will be given. And in the solver, this is the black box. The solver, what it will do, we whatever turbulence models we have imposed, it will take into consideration, and it will calculate all the mass, momentum, energy, all those things values, and it will also take into consideration of the initialization, all those things, convergence criteria, all those things it will take, and it will calculate all these values and split it into the result file. And in post processing we will have xy contours, xy graphs, xy plots, contours, velocity vectors, other kinds of results. So this is the flowchart type of representation of all the process that we have discussed till now. Now if you see the modeling softwares, these are some modeling softwares that are available. There are many other modeling softwares that are available, but these are some modeling softwares that are I have listed here. And these are some meshing softwares that are listed. ICM CFD is used in ANSYS, and ANSYS Workbench is also there, and ANSYS APDL is also there. Okay, ANSYS APDL means it is in what you say, the stress analysis. Okay, and this one is used for both stress and flow analysis, and this one is generally used for the flow analysis. And the hypermesh, these are all. So there are many there are many meshing tools, and these are only few meshing tools I have listed. So you can see how much work is going on, the modeling thing and meshing, and these are the some tools that are available in the market. Some are, this is a open source software, you don't have to purchase any license for that, but these all these things you have to purchase license. There are some other open source softwares also, and there are some other proprietary softwares also. So this is a small list, with the list is inexhaustive, so many softwares are there. And we have seen the last one, that is post processing. In post processing also there are many tools that are there. Techplot, generally most people use. I have seen many people using Techplot. I cannot say. ParaView, Iris Explorer, Field View, OpenDX. There are many n number of post processing softwares also are there. So this is about the process. So what we have discussed till now, we'll just have a recap. First we have to identify the problem. Once we have identified the problem, we have to identify what is the easiest way to solve the problem, what is the domain it should look like, and what are the boundary conditions, what are the input conditions, what is the appropriate meshing technique for that, what is the turbulence model I should use. All those things I have to give, I have to solve and see whether the solution is converged, and then I have to give the results in the form of some plots or some data. So this is the basic process of, or the basic outline of the CFD process that generally happens. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.